So today we are actually going to start where we left off last time, which was with this example right here. We're still in Chapter 1. We're going to finish that off today. I'm going to go ahead and just start from the beginning because really examples like this are not very productive, just trying to pick up from where we left off. So what we have is a circuit that looks like this, and it's because it has this capacitive element. That's what I was talking about when I referred to homework 121. This is sort of similar, so I'm hoping that we can address a lot of the points that are associated in there. Now, before I jump to this, I did want to go over a couple of things which I feel might be helpful. I wrote this down previous class. Just a couple reminders when it comes to vectors and complex values and such. I will post this, so again, write down whatever you need to, but don't get, if you don't get it all copied down, that's not a big deal. Impedance, again, we did a couple of these already. Impedance, Z, complex value equals resistance plus J times reactance. Admittance, Y, is equal to 1 over Z, is equal to conductance plus J times susceptance. Now, how do we come up with the impedances for passive components? A resistor is simply R plus J0. Capacitor, we're assuming it doesn't have an internal resistance, plus 1 over J omega C. It can also be written as 0 minus J times 1 over omega C because J is equal to negative 1 over J. When you flip it from top to bottom, it becomes negative. Omega is the frequency of the wave. J is square root of negative 1. Inductor, 0 plus J omega L, again assuming there's no internal resistance for the inductor. These few lines talk about converting from rectangular to polar form. If you have something in a rectangular form like this, the magnitude of it, we use Pythagorean's theorem. So it'll be square root of real portion squared plus imaginary portion squared. The angle will be the inverse tangent of the imaginary over the real. One thing to keep track and be mindful of here is that if you have a negative number in the denominator, your calculator will often, essentially there's no way for your calculator to know whether the negative value is in the numerator or the denominator. But they're two different values. Okay? So if you have a, I'm going to turn off my timeout here 1 second. I don't remember how to do it. All right, I'll just keep it like this. Okay, so if you do have a negative value in the denominator, you'll have to account for that by shifting by 180 degrees because it'll give you essentially the other end of the other side of the unit circle. Now, polar to rectangular, if we have a magnitude of gamma and an angle of delta, the real portion is gamma cosine delta. The imaginary portion is J, obviously, times gamma sine delta. If we're doing math, addition and multiplication, addition we want to do in rectangular form because we can simply add the real parts and the imaginary parts. Multiplication we want to do in the polar form because these two will multiply and these two will sum together. Okay? So that's just a real basic overview of how we deal with complex values and vectors and some of the different conversions and stuff that are needed, which will come into play a little bit in this problem. And when we get back around to problem 121, it'll also play in there. Yes?
When are we going to be converting from rectangle to polar?
Well, I mean, if you're doing a problem that requires addition and multiplication, whenever you want to do a multiplication, you're going to have to go from rectangular to polar in order to get it into this form. Right? Let's say you need to do this. Let's say you want to multiply right? I mean, you can do this using FOIL. This case works out, but if it were division, for example, you would need to convert this to polar form and this to polar form in order to make the math work out. In a similar vein, if you had something that looked like this, right, you're going to need to convert that to a rectangular form in order to do the addition. Another answer could be you're simply just interested in what the polar form looks like, because the polar form gives you, again, the answer that's more physically realizable in terms of what the waves look like. Okay, so now jumping back into the homework problem, or the example actually. So we have this circuit here. We want to find what is the transfer function for this circuit. We got about halfway through the problem. We want to analyze the input stage as a voltage divider. What I'm going to do is I'm going to take these two elements right here. I'm going to represent it as Zi. And so with that, the input voltage will be equal to the source voltage times Zi over Zi plus Rs. Next step, figure out what Zi is. It's the same equation we use for finding parallel combinations of resistors. Zri times Zci over the sum of the two. We're going to plug in R for Zri and 1 over j omega c for the impedance associated with the capacitor. We don't want to have fractions in the denominator. And this I made a little change here because this is actually a faster way of doing it. So we can multiply by 1 over itself using the denominator from the fraction in the denominator. So j omega ci over j omega ci, that cancels out this, and leaves us with Ri j omega ci. So we get this down here. Next, we have to insert Zi into our input stage equation. So we'll take this right here and plug it into the Zi up top. That leaves us with this. Again, we have a fraction in the denominator. We're going to want to try to eliminate that. So we'll multiply by that value again, 1 over itself. That will cancel out with this. That will cancel out with this. And we'll have to multiply this by j omega Ri ci plus 1. Now, one little thing that extra mini step I threw in here, which was kind of to agree with the book, was I multiplied by 1 over Ri on the top and the bottom in order to change the form slightly. You can see going from here to here, it's almost the exact same expression. I think this is close to where we stopped. This is the hard part of the problem. The input stage is the one that looks different from what we're used to seeing. The output stage only has resistive elements. So the output stage, what does that look like? It's this right here. So we'll have a voltage divider only involving resistors, very similar to what we're used to seeing. So VO is equal to RL over RO plus RL times mu VI. This was the dependent source that's present at the beginning of the output stage. We already have VI, so we can substitute it in down there. And what we're left with is this longer looking expression. RL mu over RO plus RL. This comes from the output stage. This fraction which comes from the input stage. And then lastly VS. So this whole thing, this is the transfer function. Question?
Could you just repeat, go back to step 3?
Sure. Yeah, no problem. So step 3, unfortunately I can't really get them both on the same screen, but right, is just analyzing the output stage. So for the output stage, we know V out is going to be equal to the input, which is mu VI, voltage divider, times RL over RO plus RL. So that's all that equation is. It's just the transfer function or the input-output relationship for the output stage. Where it gets more messy, okay, so that's this right here, okay? But then what we can do in order to get the full transfer function is to substitute in for our VI, which is right here. So we plug that in, and now we end up with the larger expression that's shown right here. And then the rest of it, I just pulled pieces to one, I kind of grouped chunks. This is all stuff from the input stage, this is all stuff from the output stage. This is all stuff from the input stage, and then you have your VS left over. So this is the transfer function. This is one of the main deliverables for this example. So next question it asks us is, what is the cutoff frequency for this amplifier? If you look at the input stage, you'll note that it looks very similar to a low-pass filter, or something like a low-pass filter. Okay, so we want to figure out for this whole process, for this whole device, what is the cutoff frequency? Now, how can we do that? There's several different ways that we could do it. We could plug in values and try to figure out where it goes down 3 decibels from the highest value. That would take a little bit longer. One way is to try to compare what we have to this form of the transfer function for a low-pass filter. So this comes directly from our notes. Okay, if you remember when I talked about low-pass filters, there was like a 2-column slide. It had transfer function for a low-pass filter, transfer function, other stuff for high-pass filter. So this is the one for the low-pass filter. Now, I took some of these pieces and I grouped them together and I called it alpha. This is not going to have any effect on the transfer function, so I'm just going to call it alpha and pull it out for a second. Now, if we look at what we have down here, we'll see that we're pretty close to the form that we need. Ignore the red. Just look at the blue for right now without the changes. So we have some k in the numerator. That's good. We have j omega times something, which is the same thing we have here. The only real problem is that we need a 1, and over here we have a 1 plus something. Right? So we need to get rid of this component and turn it into a 1. It's okay because we can always move it to the top. We can throw as much stuff into the k as we need. The k, again, is going to be the catch-all for all the real elements. So how do we do that? We can multiply by 1 over 1 plus rs over ri. So we're taking this component and we're multiplying by 1 over that. Again, this is equal to 1 because it's 1 over itself. And what ends up happening? So this will be 1 divided by 1 over rs divided by ri. This will get canceled out. This will go away. And then this will be divided by 1 plus rs over ri. So what we've done is we've divided all 3 individual components by 1 plus rs over ri. And that will give us what we're looking for, because now this will be a 1. We'll have j omega times something, and our k value will contain everything else. So this is what the form looks like. So our omega 0, our corner or cutoff frequency, will be 1 over this, right? Because the form says it's j omega over omega naught. So this is 1 over omega naught. Yeah. No problem.
How do you know that just in the
You mean this piece right here?
Yeah.
So it's really just a bookkeeping thing because I never got rid of it. It's still here. I just didn't write it out. So it really is. It's not a mathematical thing. It's just a bookkeeping thing. I just, you know what I'm saying? Like I just wanted to make everything shorter, so I just put it in its own little spot. But in the end, I can bring it back in and make sure that. Anyway, I guess the main point is it's there the whole time. I just didn't write it out every time. You said some other questions, or that was it? Okay. So yeah, I mean, in the end, if you actually, and we'll do this, I'll rewrite this k value and I'll expand the alpha just to make sure that it goes back into the final solution. Okay. So we have our 1 over omega 0, so that's that. And then everything else is k. K is alpha times this. So let's take a look at what we have. So I am going to put alpha back in. So that means that k will be RL mu over RO plus RL times 1 plus so now our alpha's back. And then the omega naught is this value right here. In the book they use this version of it, which is just essentially if you multiply both the top and the bottom by Ri, it gives you that. But you could just write it like this. So, the reason why I pulled out the iPad to do this one is because it's a little bit more of an in-depth problem. It requires some more advanced algebra. It requires you to keep, it's a good math problem, essentially. So I definitely recommend you take a look at this. I'll post it online. And then, we can come back to an example like a homework problem like 121 next time. But I think this sheds a lot of light on similar types of problems. Yes?
So how do you know that that denominator is what 1 over W naught is?
So you have to compare it to this right here. So you see the form for the low-pass filter, you have j omega over omega naught. So you have j omega over omega naught. So this whole thing, you're just comparing this to this form. It's all comparisons. 1 plus j omega over omega naught. K is what's up top. So that's the reason why the k is everything that was up top, and the omega naught is just the coefficient of the j omega.
Oh, even like with the numerator, because that whole thing is equivalent to it?
Yes.
Okay.
Yeah. So it's just a comparison to the table and once you get it in the same form, then you can just pull out the values. So getting it in the same form was the difficult part. All right? Take a look at it. If there's questions, I'll be more than happy to dive into it. Well, I don't know how much more I can. Well, I'll address questions. Let's put it that way. Okay? And so if you do want to see another version of this problem done, you can look at it in the lecture notes. It's done with the same level of detail. This slide is essentially just plugging in some numbers that they gave us in order to get the actual values. Because they gave us mu, they gave us RL, RO, You can get the corner frequency, et cetera, et cetera. So take a look at this on your own. I think that we spent a lot of time on this problem, so this stuff hopefully will not be as taxing as the beginning part. They ask us in the later parts of the problem also to define the transfer function for a sine wave with a frequency of 100 radians per second. So that's easy, because all we have to do now is anytime we see an omega, plug in 100 radians per second, and you'll get your values. So at 100 radians per second, you end up with a k value of 100 and a phase shift of 0. So I'll leave this up to you. Take a look. These are just plugging in the values. Okay. So yes.
Just really quickly, is the transfer function of like a specific filter usually something that's like given, or that we need to like find out?
Depends on what the problem is. So for example, if it's a low pass or a high pass filter, like very basic, then on your cheat sheet you'll have a table for it, and you can just glance at it. If it's something like what we just looked at, right, you had to derive the transfer function for that one. So, yeah, I mean, it really depends. Some problems may give you the transfer function, ask you to work with it, and ask you some questions about it. Then other types of questions may just give you the circuit and say, hey, come up with the transfer function. Okay, so the very end of chapter 1 here, a couple of important terms. Internal capacitances cause fall-off of gain at high frequencies, and this is very similar to what we saw in the previous example, right? When we have an internal capacitance, it makes the input stage look like a low-pass filter or have that sort of low-pass filter characteristic. And so you have the gain fall off at high frequencies. This is something you often see in real-life amplifiers. Real amplifiers often do have a capacitive input characteristic, which means that to work at really high frequencies, you will need better and better amplifiers. Coupling capacitors cause the fall-off of gain at low frequencies. And this is different. This is if you were to place a capacitor between two stages of an amplifier. So let's say, for example, you have those coupling, the cascaded amplifiers. If you were to place coupling capacitors between the stages, they would be series elements. Then that would cause the fall off. It would essentially block the lower frequencies. And one reason why you would do this, does anybody know why you would want to do that? One of the main reasons you would do this is to remove DC offsets. Right? If you have a DC offset and you want to bring it back down to 0, a coupling capacitor would allow you to do that. So directly coupled amplifiers allow passage of low frequencies. Capacitively coupled amplifiers allow passage of high frequencies. And what you can do is you can tune the amplifiers using some ratio of the internal capacitance that's naturally found in the amplifier. You can add more because you can always put a shunt capacitor at the input, as well as the series element. Anyway, you can use all of those together in order to tune the band of the amplifier. I would go more into this topic, but it's not really touched heavily upon in the rest of the material that we're going to talk about. So again, I'll refer you to the textbook to read up more on that. This is something that could show up on that oral quiz as sort of a short answer, but as you'll see, this is sort of where this material ends. Okay, the conclusion I encourage you to take a look at. I'm not going to read through it line by line, but really what we went over in this chapter 1, it was our warm-up to the class. I know it was a pretty brisk warm-up. It wasn't like it was easy, but it got a lot of topics back in our mind, refreshed us analog, digital, harmonics, how to work with basic amplifier representations, a little bit of stuff on vectors and dealing with complex impedances. So the good news is we're not going to stop using these things. So what you have learned about over the past week or have been refreshed about over the past week, we're going to keep using that so you'll have more opportunities to improve your skills. Okay. So now chapter 2. So we're going to, I don't want to say slow it down, but we are going to be addressing now material that moves in a more linear fashion. There's not going to be as much jumping back and forth between frequency spectrum, Fourier series, amplifiers, all this type of stuff. This is now for the rest of the class going to follow a pretty linear path. There still is going to be a lot of repetition from this chapter as compared to ENG212, the circuits class, because we did talk about amplifiers a decent amount there, but we are going to go further than we did. So signals and amplifiers, which I think was, unfortunately, the title for chapter 1 was the same thing. That should be changed. So what are we going to learn about? The terminal characteristics of an ideal op-amp, how to analyze circuits that contain op-amps, resistors, and capacitors, how to use op-amps to design, let's say, those that address more specific design characteristics, more sophisticated op-amp circuits, and talking more about the non-ideal characteristics of op-amps. The basic setup of an amplifier, 5 terminals. In a practical amplifier, you will see there are other terminals that aren't necessarily shown here. Offset, bias, nulling terminals, things of that nature, which we'll talk about at the end of the chapter. But it's not part of our most basic representation, most basic model of how an amplifier looks. So you have your non-inverting and your inverting input. You have your positive and your negative supplies. And then you have your output. Generally, your output is single-ended, meaning that it's referenced to the ground of your supplies. The input is differential, meaning that they're referenced to one another. The amplified value is this minus this. Hopefully, you all remember the ideal characteristics of an op-amp. The ideal input characteristic is an infinite impedance, an open circuit. The ideal output characteristic is a zero impedance. The differential gain, A, is infinite. This is always one that maybe throws students for a loop a little bit because practically, it doesn't make much sense. Why would you want an infinite gain, ideally? The bandwidth should be constant over the entire frequency spectrum, from DC all the way to infinitely high frequencies. So ideally, V3 is equal to A, which is our ideal gain, times the difference between the non-inverting and the inverting inputs. So then the question I ask is an amplifier with infinite gain of any use to us? There's a couple applications where it is useful. One of them is the comparator. But more times than not, no, it's not useful, right? We want to have a finite gain. So what do we use in order to bring the gain down to a finite number, finite value? This we definitely talked about in circuits. So we didn't...
Like a certain set of resistors.
External resistances, yes, which we call... It's the ratio of those resistors. There's another word, something loop. Feedback. We have a negative feedback loop. So what we do is we take the output, we attach some external resistors, like you said, which provides negative feedback because we connect it to the inverting terminal. That reduces the gain down from an infinite value to some finite value. And the ratio between those resistors is what determines our gain ultimately. So this is a picture from the book, simply just showing some of the ideal characteristics. Again, the input impedances are infinite, so there's no current flowing into the input terminals. The output impedance is 0. So what you get the output is just directly the gain times the difference between V2 and V1. You'll note here, this is what we call an open loop configuration because we don't have any negative feedback applied yet. We're going to talk about this more in a second, and this is one thing we did not talk about in circuits. Differential versus common mode input. So our differential input is the difference between the inputs at the inverting and the non-inverting terminals. The common mode input is that which is present at both. So let's say you have an input of 10.1 and 9.9. The differential input is going to be 0.2. 10.1 minus 9.9, 0.2. The common mode input is going to be that which is common to both of them, or the average. So the common mode input will be 10. Let's say you have positive 0.1 and negative 0.1. Differential input is the same, 0.2. But in that case, the common mode input is 0. Generally, we want to amplify only the differential input, not the common mode input. So we want our differential gain, that which is applied to the differential input, to be whatever value we define. Normally, we want the common mode gain, which is applied to the common mode input, to be very small, or 0, ideally. That's another ideal characteristic of an amplifier, is that our common mode gain is very low, is 0. And so just a repeat of the characteristics of the ideal op-amp. These are very important to know. I say in this class, there's not much need for memorization, but this is something that you should know off the top of your head. Again, infinite input impedance, 0 output impedance, 0 common mode gain, which we call complete common mode rejection. It rejects the common mode input completely. Whether you have 10.1 and 9.9, or 0.1 and negative 0.1, you should get the same output for both of those cases, ideally. Infinite open loop gain and infinite bandwidth. Right, the common mode, I already said this, the common mode input is the average of the V1 and V2, which is the input at the inverting and the non-inverting terminals. And you can use these equations to go from, so this takes you from V1, V2 to the common mode input. These move in the other direction. They take you from the common mode input to V1 and V2. The differential input is simply, I didn't write it on here, but it's V2 minus V1. This is a picture from the book that illustrates those equations. I don't necessarily find it that much more, it's not that much easier to understand than the math, but I think the math is actually easier to understand than this picture. Okay. So what are our two basic closed loop op-amp configurations that employ op-amp and resistors alone? Yes?
What would be like the circumstances to wanting to use the differential input versus the common mode input?
So the rule of thumb I would say is you normally don't want to use the common mode input. That's like 99.9% of cases. So you usually always just want to amplify the differential input. Okay, so the two most basic closed loop op-amp configurations are the inverting and the non-inverting op-amp. These are the first two that we learned in ELC251-03. These are the ones that you employed predominantly in ELC251-04, and it's the starting point. So I want to erase where I marked this up. Okay. So, this, which one is this? An inverting or a non-inverting? Does it say? Oh, okay, well, okay. Let me ask a follow-up question then. How can you tell whether it's an inverting or non-inverting? Yes?
What's the feedback you're going into the input, the inverting input?
Actually, no. Sorry to ping you on that. The feedback will always go into the inverting terminal because we're using negative feedback.
The input voltage is going into the negative terminal?
That's the thing. So for the non-inverting, this will be grounded right here, and we'll have our input going to the non-inverting terminal. Remember, we always want to use negative feedback. If we connect this feedback to the positive terminal, then we'll be providing positive feedback, which will, in effect, increase the gain from what is already ideally a very high gain. So that's not going to help us too much. So how does this work? This connection, R2, facilitates the negative feedback. Right? So the current flowing along this path, more current flowing along this path will cause more feedback, more negative feedback, which will further reduce the gain. When the current reaches this point right here, it cannot go to the right. We are again assuming an ideal op-amp, which means that there's no path here. This is an infinite input impedance, which means all the current needs to flow like this, to the left. That's why we say R1 regulates the level of feedback. Because if R1 is small, a lot of current can flow in this direction. If R1 is large, it's going to cause less current to flow along that path. Right? That's just basic Ohm's law. Larger resistances mean less current flow. Smaller resistances mean more current flow. So that's the role of those two. R1 is that which facilitates the feedback. R1 regulates the level of the feedback. And this makes sense if you think about like the gain expression for an inverting op-amp, negative R2 over R1, right? R2, a higher value, means more negative feedback. You get a more negative value. R1 is in the denominator, and it regulates the level of feedback. And then the other stuff, right? Obviously, the source is applied to the inverting input for the inverting op-amp, and the non-inverting input is going to be grounded. Sometimes we will put a resistor right here, which is equal to the parallel combination of those two resistances together, which will allow us to eliminate some nonlinearity. Let me just go ahead and delete all these comments in one swoop. Okay. So, returning to this. So now how do we analyze the closed loop gain for an inverting configuration of an op-amp? I think that we did this in ELC251-02. Is that correct? We talked about how we can look at the circuit and we can calculate the closed loop gain for any type of closed loop configuration. Now, for the inverting and the non-inverting, we already know what the answer is, but we can go through the steps in order to determine it. So the first thing we're going to do is we begin at the output terminal. And what we say, and when we do this process, we're going to be picking out pieces of the ideal characteristics of the op-amp and using them. So, this one is the one that I think throws students for the most loop. If V out is finite, then the differential input must be equal to 0. So what does that mean? This right here is just taken from our ideal characteristics of an op-amp. V2 minus V1 times A equals V out. Right? A is ideally infinite. We want a finite output. So there's only one value or set of values here that will give us a finite output. There's only one thing you can multiply by infinity to get a finite value, and that's 0. So V2 minus V1 will be equal to 0 because we want V out to be finite and because the ideal gain is infinite. And what this does is this will be visualized as a virtual short between V1 and V2, the inverting and non-inverting terminals of the op-amp. Step 3, and I'm going to go through this verbally, and then we're going to show a picture, and we'll do it visually as well. Step 3 is to define the current moving into the input. And we know that the current moving into the input will be equal to 0. So what this means is that the rest of the current will, like I said a second ago, will flow along the feedback resistance and to the left towards the source. So now let's look at this visually. So let's take a look at this right here. So what changes do we make to this circuit in order to essentially remove the op-amp from the picture? That's what we want to do. We want to remove the op-amp and get a circuit that's only based on sources and resistors, and we know how to solve that. So again, right, we know there's a virtual short here because of what we said about the output having to be finite. So V1 and V2 are at the same potential, but there is not a short here. There's a difference. What that means is current cannot flow along this path. We know that V1 is equal to 0, but if we were to apply KCL at this terminal, there would only be one input, one output. We also know that no current can flow in here. No current can flow to the right, which means that all the current has to flow like this, or as I have it shown, flowing like this. It's the same, either direction. And what we're going to do is define that as I1. Once we make those two changes, right, you can see the op-amp no longer has an effect on what's going on in the circuit. We can derive the gain by simply looking at this path right here with the knowledge that V1 is equal to 0. So this now is what we have to solve. And so in order to solve that, we'll apply KVL. We know that V out will be equal to V in minus R1 plus R2 times this current I1. Right? There's another equation that we know. We also know that I1 will be equal to this minus 0 over R1 because of that virtual short right there. So two different equations that we have. And so that's what's shown here. We see that V out is equal to, we could say V in minus both the drop across both of the resistances, or we could start applying KVL from right here and simply say V out is equal to 0 minus I1 R2 and just use half the path. So that's what I've done. V out equals V1, which we know is 0, minus I1 R2. And so we're left with one piece here. We don't know what I1 is. I1, if we go back to the previous slide for a second, we know that I1 is equal to V in divided by R1, because this is 0. So V in divided by I1, V in divided by R1 gives us I1. So we substitute that in here. So we end up with negative R2 times V in divided by R1, and that gives us this, which is shown right here. And so this is one of the most fundamental expressions that we're going to see in this course. Negative R2 over R1 is the gain for the inverting op-amp. Now this picture here does a really good job. It's one of the best pictures in the book. Does a really good job of showing you all the steps of what we just did. Again, V out, okay, well this is the output. We're going to follow the numbers because the numbers show you the steps. Step number 1, apply the virtual short. So we know there's a 0 volt differential between the two terminals. Step number 2, well, step number 1 and step number 2 are really the same step. They're saying apply the virtual ground. Okay. Step number 3, we know I1 is equal to V in divided by R1. Step number 4, figure out that there's no current flowing into the op-amp because it has an infinite input characteristic. Step number 5, apply KVL to this path here. We know that I2 equals I1 will be equal to VI over R1. And then the last step is to apply KVL. We know that 0 minus the voltage drop across here will be equal to V out. This equation will substitute in this, pull it in down here, and we end up with that. Like most things in this or any other class, once we go over the example, it becomes a lot clearer. So this is sort of the first pass view at how to do this. This is a good figure. If you can understand what this figure is trying to tell you, it does give a pretty good summary of how to do it. But again, we'll go through a bunch of examples, and I think that'll make it a little bit clearer, and you can have an opportunity to ask some questions. Okay, so the ideal gain is negative R2 over R1 for the inverting type op-amp. What happens if the gain, the open loop gain, the internal gain, A, is not infinite? So this right here only works when we can assume that A equals infinity. If A doesn't equal infinity, and we're not going to derive this expression, but they give it to us. This is another expression that we can use. So the R2 and the R1 values you already know. The only thing you need to plug in is the A value. You'll note that if we plug in A equals infinity, this term goes away, and what we're left with is our ideal expression. So this is one that you'll have on your cheat sheet. You should be familiar with it, know how to use it, but again, we're not going to derive it. So you just need to know that you should plug in the appropriate value of A. Yeah?
What would the gain be then? Like, because isn't the gain V out over V in? Like,
So the gain is still going to be V out over V in, regardless. It's just what's the numerical value of that. If you have a non-infinite value of A, you'll have to take that into account when you calculate. Same thing, and the same way that you use this right here. If I asked you what's the gain, it's V out over V in, but you calculate numerically using R2 and R1. If A is not infinite, then you have to use this little bit more of a complicated version of the expression. And so what's the rule of thumb that we're going to employ of whether we use door number 1 or whether we use door number 2? Essentially, it's this. If 1 plus R2 over R1 is much less than A, then we can simply use this one. If it's not, then we got to use the bigger one. I use this rule of thumb as 100 times difference, 2 orders of magnitude. The book seems to lean more to just use a 10 times difference, 1 order of magnitude. But again, it's a soft boundary anyway, because the closer these two get together, the less accurate this expression is going to be. It's not like there's some hard boundary where it becomes, wrong to use the ideal expression.